Yeah, now it is preparing today.
Yeah, now, okay. Very warm welcome. Welcome to the Satellite Meteorology Weekly online series, lecture series jointly organized by South Asian Meteorological Association and Birla Institute of Technology, Mesra, India. So today it will be our fourth lecture. It will be given by Dr. Atul Kumar Varma. Before that, I would like to invite Professor Dr. Someshwar Das, Secretary of SAMA, to giving the welcome address. Sir, stage is yours.
Okay, thank you, Dr. Swagata. ABM Dr. Tyagi Saab, President of the SAMA. Dr. R.C. Bhatia Saab, the Chairman of the Advisory Panel of the Lecture Series. Today's distinguished speaker, Dr. Atul Kumar Varma, Group Director and Scientist G, Atmospheric and Oceanic Sciences, Oceanic and Applications Group, Space Application Center, ISRO, Ahmedabad. Distinguished members of the organizing committee, distinguished participants from more than 60 countries, I should say, more than 59, 60 countries. Ladies and gentlemen, we welcome you once again on behalf of the South Asian Meteorological Association, SAMA, and Birla Institute of Technology, BIT, Mesra. I see that since last week, some more people have joined or registered for this lecture series. So the total number of registration is now more than 1,760. Exact figure is 1,761. And also I see that there are a good number of views of the past three lectures. Today is the fourth lecture. So for the past three lectures have been viewed by good number of people. The first lecture given by Dr. Kelkar Sahab and Dr. Rajkumar Sharma Sahab were viewed by, I think, almost 2,221 people. The second lecture by Bhatia Sahab has been viewed by 897 people, and last week's lecture by Dr. Suchita Srivastava has been viewed by 447 people. And all these numbers are, of course, increasing day by day. So there is a good number of views by the people. That means our lectures are very, very popular in the public in all these countries. So since some new members who registered just this week, I would like to repeat some of the things which I mentioned already in the last week. That means, as you know, this is the fourth lecture, this series of 20 lectures that we have planned. This is a continuation of our efforts on capacity building of the people of this region. Many of you know that we conducted the first online lecture series on atmospheric physics jointly with the SRM Institute of Science and Technology, Chennai, for 4 months during January to April 2023, in which more than 2,000 people had registered from about 48 countries. Then the second lecture series or the second training course that we conducted was on the modeling and WP modeling, basically training on WRF modeling. It was jointly conducted by the CDAC, which is the Center for Development of Advanced Computing in India. And that was conducted for 3 weeks with online hands-on practicals remotely from all those countries, I mean, from our SAARC countries basically, to the HPC of the CDAC. And this one is a third training series on the satellite meteorology that we have started from 2nd of this month, 2nd of September. And, you know, we have a distinguished panel of very senior scientists and professionals from reputed institutions of this region who are experts in the field. The syllabus of the lecture series has been designed based upon the feedback and requirements of the member countries of SAMA. This lecture series is targeted to postgraduate students and professionals of non-meteorological background who are interested in learning the subject of satellite meteorology. As you know, this lecture series will continue for 5 months, 20 weeks. That means from 2nd of September, that is started already, till 20th of June 2024. As announced earlier, at the end of the lecture, we shall provide certificates to the participants who will attend all the lectures with at least 75% attendance. And those who are interested in receiving certificates with the grades like outstanding or excellent, etc., they will have to appear in a test which will be conducted at the end of the lecture series. So, as you know, these lectures are also live streamed on the YouTube. The recorded lectures will be available even after the lectures are over. For people who could not view live of the time difference between India and other countries, so they can always watch anytime when they are free. So we shall have a interaction session for question and answer at the end of the lecture. All the participants are requested to write their questions on the chat box so that our organizing committee members will take up the questions at the end of the lecture, and the speaker will try to answer them. So enjoy the lecture and have a good time. Thank you, Dr. Swagata, on to you.
Thank you, sir. Thank you for all the details about that initiative of SAMA, along with sometimes SRM, sometimes CDAC, sometimes BAT and all others. Now, I would like to invite our President, AVM Dr. Ajit Tyagi, sir. Sir, please give us your vision, share your viewers.
Thank you, Dr. Swagata, and I join Professor Someshwar Das in welcoming all the participants, and special thanks to our...
Dr.
Am I audible?
Yeah.
Yes, sir.
Okay. A special thanks to our speaker of the day, the resource person, Dr. Atul Kumar Varma ji, for having given his consent to deliver this talk. There wouldn't have been a better expert, teacher, scientist who could have covered the topic, which is today's talk, remote sensing of microwave-based sensors of the weather satellites and its products. We had the first lecture, last lecture by Suchita, which gave fundamentals of remote sensing, and this is a logical next level to cover. To tell about Dr. Varma, who is Group Director and Head of the Atmospheric and Meteorology Group. He is a scientist with hands-on both in the research, application, and products development. So immense contribution for the meteorological community through his work in the SAC. So you see, this is a grand mix of research come application. So, and ISRO is, as such, is a leading as far as the capacity building is concerned on online programs they conduct. And so the support given by SEC to our this online series is really commendable, and we feel very happy and confident that our online lecture series also will be of immense use to the participants from some 50 odd countries. So thank you so much to the SEC management and the scientists who are will be delivering the lectures in coming weeks. In fact, we are happy to have Dr. Thaplial, who is a member of our Satellite Met committee chaired by Bhatia Saab. So they have planned this lecture series very well, taking feedback and inputs from the member countries, what are their training requirements. So this is a very practical oriented program, and with the experts in the field from SAC, IRS, and NRSC and India Met Department. There would have been a good mix of faculty to conduct this online program. As Professor Somesh has mentioned, we are receiving a good response both online and through YouTube, who are making use of these lectures. And in the future, I think this number is going to increase exponentially as people come to know. So thank you so much to Bhatia Saab and Thaplial and other Satellite Met group who have conceived this, the organizing committee who are doing such a wonderful job. And top of it, it is the resource persons. And thank you to Varmaji from out of your busy schedule on Saturday afternoon to have given your consent to deliver this talk. And we look forward, and I'm sure it will be great help to the participants to understand the microwave remote sensing by your lecture. Thank you, and I request all participants to make best use of it. There is a question answer session. Ask some questions, and thereafter also through email we'll request Dr. Varma to respond to the queries which participants may have. Thank you so much. Have a great time.
Thank you, sir. I also strongly believe that the growth of SAMA will continue with the great research person like today, Dr. Atul Kumar Varma. So today the introduction of the speaker of lecture will be done by Dr. Poulomi Chakraborty, one of the active member of the SAMA. So Poulomi, now you can continue.
Thank you, sir. Good afternoon, everyone. I'm sharing my screen. I hope it's visible.
Yeah.
Good afternoon, all distinguished panelists and our guests. We are truly honored to have an eminent personality grace our SAMA BIT Mesra weekly online lecture series on satellite meteorology. Please allow me to introduce Dr. Atul Kumar Varma. He is the Group Director and Scientist G at the Atmospheric and Oceanic Sciences and Applications Group at the renowned Space Applications Center, ISRO, Ahmedabad, India. His pivotal roles also include serving as the Deputy Project Director for OceanSat 3 and INSAT 3DR and 3DS. A distinguished alumnus of institutions like Florida State University, IIT BHU, IIT Kharagpur, his academic journey spans from Lucknow University to a postdoctoral stint in the USA. With an astonishing 36 years in satellite remote sensing, Dr. Varma's research primarily delves into atmospheric radiative transfer and retrieval of geophysical parameters using satellite IR and microwave observations, remote sensing of precipitation in clouds, atmospheric process studies, and numerical modeling, observational studies, and mathematical modeling of ocean surface and subsurface waves. He has enriched the scientific community with over 200 publications, 90 of which are in distinguished peer-reviewed journals. Additionally, his contributions include algorithm documents, ISRO reports, and book chapters. Dr. Varma's accolades are a testament to his contributions. For being elected a Fellow of the Royal Meteorological Society, London, to earning the NASA Group Achievement Award 2015 for Global Precipitation Measurement, and numerous ISRO Team Excellence Awards, his achievements speak volumes. His collaborations with international missions and organizations like NASA, CEOS, and CGMS are a testimony to his global repute. Dr. Varma has also represented India in Quad nations, that is Australia, Japan, India, and US, Space Working Group as a technical lead and steering committee member. Currently, he is an associate editor for the Journal of Indian Society of Remote Sensing, enriching the academic community further. Join me in extending a warm welcome to Dr. Atul Kumar Varma as he shares his vast knowledge and experiences in satellite meteorology with us today. Welcome, sir.
Thank you, Dr. Poulomi. So today, Dr. Atul Kumar Varma sir is going to talk about fundamental principles of microwave-based remote sensing using meteorological satellites and products available and their application-based system. Yes, now stage is yours. We all are eagerly waiting to listen your talk. Sir, you are mute. Sir, you are mute.
Yeah. Dr. Ajit Tyagi ji, Dr. Someshwar Das ji, Dr. Swagata, Dr. Poulomi Chakraborty ji, and Dr. Mohan Kumar Das ji, ladies and gentlemen, good afternoon. And I first thank Dr. Poulomi for giving so nice introduction. This is an honor and privilege for me to deliver this talk here. I thank both Sama and BITS Mesra for this opportunity given to me. Now I start my talk. I share my screen first. Yeah.
Yeah, perfectly fine.
Okay. Yeah, I think now it is visible to all of you, right?
Yes, sir.
Okay. Yeah, so today I am speaking on the fundamental principle of the microwave-based remote sensing using the meteorological satellites and products and their applications. So this the figure here, what you see here where I'm moving my cursor. This is the absorption spectra of the microwave ranging from the not the microwave, for the electromagnetic waves ranging from the ultraviolet to the microwave. Right side, you are seeing the microwave. Here, the gray area that you see is actually representing the absorption, and the white area that you see is actually where the absorption is minimum, and this region we called the window. Here we are interested in the microwave part of the electromagnetic spectrum. So this is you can see with the red box. This red box is shown here too. In the microwave, if you move to the microwave part of the electromagnetic regime, then here you have that absorption by only oxygen and the water vapor. There are two absorption lines of the water vapor at 22.235 gigahertz and 181.31 gigahertz. There is also absorption by the oxygen. There are a number of lines existing between 50 and 64 gigahertz, and this is we call the oxygen continuum. And there is another weak absorption line at 118.75 gigahertz. Apart from that, the microwave, there is no absorption by any other atmospheric constituents like gases, trace gases and all. The microwave that we roughly define is actually the frequency from say 1 gigahertz to 300 gigahertz. All the microwave instruments working in this range of the frequency. There are two types of microwave instruments, satellite-borne microwave instruments. One set is called the passive instruments, another set is called the active instruments. Passive instruments are those who measure, they are actually only the receivers, and they measure the radiances which are emanating from the below. They don't carry their own source of energy. On the other hand, the active sensors are those which carry their own source of energy. They are essentially the radar systems. So this altimeter, centrifugal aperture radar, and spectrometer are the radar systems. There is one more system that is called a GNSS, radio occultation or reflectivity. This is actually unlike the other radar system. This you can consider is bistatic, whereas other you can consider as monostatic. It is called the bistatic because here the transmitter is on GNSS satellite. GNSS for students. This is called the Global Navigation Satellite System. So here the remote sensing is done using the network of the GNSS satellites. So this GNSS, the transmitter is on GNSS satellite, but the receiver is in another satellite, which is a low orbiting satellite. So this is another kind of concept, and this you can consider as bistatic system. What the microwave can provide, what are the measurements it can provide? Here I have listed them. One side is the passive instrument, what the passive instruments can provide, and right hand side you can see what the active systems can provide. You can see these passive and active microwave together can provide a large number of geophysical parameters related to the atmosphere and ocean. I have included ocean also because ocean and atmosphere are the coupled systems, and this is very difficult sometimes to differentiate whether this particular parameter is useful for studying the atmosphere or for oceanography. For example, the wind over the oceans. So that, oceanographers also use it to force their model, whereas the meteorologists also use it. So this is covering both atmospheric and oceanic systems. So here you can see, I'm not reading out all of them. You can see that large number of parameters can be obtained from the microwave instruments. This is showing that what the India has contributed to the microwave satellites. We have started our journey in 1979. That is about 45 years back, when India first launched Bhaskara-1 satellite with a micro radiometer called the Samir. And that carried a 2-frequency radiometer operating at 19 and 22 gigahertz frequencies. Then in Bhaskara-2, there was Samir. Again, Samir was put in the Bhaskara-2, and one more frequency was added to it, that was 31 gigahertz. Then after, we have now moving ahead with the different satellites and sensors, and present time we have the Oceansat 3, which was launched last year in November, and it is carrying a active microwave instrument called the scatometer. I will talk about this instrument later in my later part of my talk. In the microwave, first I will cover the passive microwave instruments, that is the microwave radiometer and the sounders. So microwave radiometers are operating in a number of frequencies. These frequencies we cannot select as and when we like, because there is an international committee called the International Telecommunication Union. They allocate the frequencies for different purposes. As you know, that microwave can be used for many purposes. It can be used for communication, navigation, radar, surveillance, and many other purposes. So because there should not be interference in the microwave used by one instrument for one purpose to another instrument used for another purpose. So frequencies are allotted for different purposes. So we have to operate with the frequencies that are provided for the remote sensing purpose. So here the different frequencies, common frequencies which are available, or frequency bands that are available, instruments are operated in those frequency bands. There may be slight different, instruments may be operating in with slight difference in their operating frequency. For example, some instrument may operate at 10 gigahertz, another may operate at 11 gigahertz, but they will be within a small band. So coming to the next slide, as people believe that microwave measurements are the all-weather measurements. That means if you are working with the microwave, you need not to worry about the cloud precipitation, etc. You can still get the measurements. But that is partly true, because microwave are also attenuated by the clouds and the precipitation. Here you can see the figure on left-hand side that is showing the effect of clouds on microwave. Ice clouds are mostly transparent, but other clouds, convective or stratiform or whatever, or mixed type of clouds, they significantly attenuate the microwave frequencies. Particularly if you move to the higher frequencies, then you have the more attenuation. But if you are moving to the lower frequencies, for example, the L band that is at 1.4 gigahertz, 4 gigahertz, there you have almost atmosphere transparent for microwave in cloud, also in case of the rain. Here also you can see if you are operating at 3 gigahertz, it is almost transparent, but as you move to the higher frequencies, the 30 gigahertz, there is a substantial attenuation of the microwaves in that. Now coming to the how much microwave can penetrate in the ground. See, ocean, the microwave does not penetrate. It penetrates, it only provides you you can call it the skin skin information, or slightly few millimeter it can penetrate. But over the land, it can penetrate depending upon the frequency at which you are operating or the type of the soil there. If the soil, and also the soil moisture. If the soil moisture is low, then the penetration can be higher. If soil moisture is more, penetration is less. If the frequency is low, then you have the more penetration. But if frequency is large, say if you're operating at 10 gigahertz, 14 gigahertz, or 18 gigahertz, then your penetration is very small. You will get only the surface information. So this is about how microwave is affected by the atmospheric constituents like precipitation or the cloud particles, and how they are affected by the different land types. What is their penetration? Here on here in the third figure on right hand side, what is plotted here is skin depth. Skin depth is actually representing the depth by which energy is reduced by 1 upon E times of its original value. So this is how the skin depth is defined. So this is actually the measurement of the penetration. Now, how the microwave work? Microwave, unlike the optical instruments where the energy is collected by the optical systems like lens and all, here the energy is collected by the antenna. When you are collecting the energy by the antenna, the resolution that you will achieve with the microwave, that depends upon the beam width. Beam width in turn depends upon the size of the antenna. So here what you can see, beta, that is lambda by L. Lambda is the operating wavelength, and the L is the aperture size, antenna aperture size. If antenna size is large, then you have a better smaller pixel size, better resolution. But if your antenna size is small, then you have the problem. If you do little bit of, and the resolution, which is the row here, that depends upon the beam width as well as the range at which you are going to make the measurements. So beta into R. So here, if you do little bit of calculations, you will see that, small, very simple calculations. If you do the calculations, you will find that, for example, if you're operating at the 3 gigahertz, the 3 gigahertz means lambda is about 10 centimeter. And to achieve the 1 kilometer resolution, your antenna size should be 100 meter, which is not practically possible. We have the antenna of few meter of size. We cannot carry very large size antenna on the spacecraft, as a result of which in the microwave we have very coarser resolution, particularly for radiometers. We have very poor resolution. So micro resolution is always in terms of tens of kilometer. If you are operating in say low microwave frequencies, say 10 gigahertz, 19 gigahertz, or 37 gigahertz. But if you are operating at say 85 gigahertz or 157 gigahertz or 183 gigahertz, then you can achieve a better resolution of the order of 5-6 kilometer. So we have to contend with this kind of limitation because of this engineering involved or science involved. Now coming to the macroradiometry. Now I am moving to the macroradiometry. This started with the Planck's function. This what you see here on the screen, this equation is actually the Planck function. This is given by the Max Planck in 1900, a German physicist who provided the spectral energy distribution of the radiation emitted by a black body. So this is the spectral energy which is emitted by a black body. Here, what you see, H is the Planck's constant, mu is the operating frequency, and Kb is the Stephen-Boltzmann constant, and T is the temperature and absolute temperature in Kelvin, and C is the speed of light. So what you see here, it is a nonlinear function of T, and here T, it varies only with the T. Now, for the microwave, you can simplify it. Suppose you take this in the denominator, this e to the power h mu upon kb by t. If you try to expand it, let us assume that h mu by kb t is x. Then you can expand it. What is in this bracket? You can expand it like this. And here, if you assume that x is very, very small, or in our case, in the case of the microwave, h mu upon kb by t is very, very small, then it simplifies into something called a Rayleigh-Jeans law, where the emitted energy, spectral energy, is a linear function of temperature at a given frequency or wavelength. So in the microwave, often you will see that equations are written, ray transfer equations are written, not in terms of the brightness, but in terms of the temperature TV. So that is the reason, because it is linearly related to the B. And this is for a black body, but we know that all earthly objects are not black body. So in that case, the concept of emissivity comes into the picture. So and the concept of the brightest temperature come into the picture. Brightest temperature TV is nothing, emissivity times the T. So you will see the most of the ray transfer equations are written in terms of the brightness temperature, not in terms of the temperature or the brightness B. So this is one thing. Now coming to the ray transfer equation in the microwave. You see, this equation that I have written here is valid not only for microwave, for IR also. Here, only thing is scattering is not taken into consideration. Now, let us assume that atmosphere comprises of different layers, as I have shown in a figure on right hand side. These layers are of not same depth, because this is in terms of the pressure, equal pressure lines. And we assume that atmosphere is like this. Now, let us think about radiations that are reaching to the satellite, which is at about 800 kilometer or 1000 kilometer above the surface of the Earth. What it will be receiving it? The satellite will be receiving the radiations that are emitting from the surface. That is the first term in this equation. So radiations emitted from the surface are given by the Planck's function. Now, this will again has to be multiplied by the emissivity of the surface, E mu. Then when it will be moving through the atmosphere, the transmission of the atmosphere will play its role to attenuate it. So you have to multiply the total transmission of the atmosphere from surface pressure P as the surface pressure to the top of the atmosphere where pressure is 0. So PS to the 0. So this is the first term in the transfer equation, that is the energy coming from the surface reaching to the satellite. Now, second term is coming because there are different layers of the atmosphere. Each layer is also radiating, and that radiations are also going directly to the satellite. So each layer will have its own temperature. So again, you have the Planck function there, and you again have the transmission from that particular layer to the top of the atmosphere. So you have to multiply with that, and you have to integrate it for all the layers, starting from the surface to the top of the atmosphere, because all layers are radiating. So you have to integrate it. This is the direct atmospheric emission reaching to the satellite from the from the atmosphere. Now, these layers are also radiating downward, not towards satellite, but towards the Earth. So what will be this will be, how much radiation will be coming towards the Earth? That will be same, the mathematical form will be same as you have, as you have in case of, radiation which are directly going. Only thing is now you have to integrate it from 0 to surface. Okay. And here, but what happens when these radiations are reaching to the surface? They are reflected. So you have to multiply it with the reflectivity of the surface. Reflectivity is actually in the microwave 1 minus emissivity, because we assume transmittivity is 0 below the surface. So 1 minus emissivity you have to multiply. Then you have to multiply it with the transmission of the atmosphere, total transmission from surface to the top of the atmosphere. So that is also done. This is the rate transfer equation. Here in microwave, scattering does not take place other than that from the rain and the clouds. Otherwise, for all other atmospheric constituents, scattering is not considered at all. So we don't have the scattering term here. But when you are studying the precipitation or say cloud, you have to take into consideration the scattering. Here in this figure, where I am moving my cursor, I think you can see that here it is shown that how the scattering from different atmospheric constituents is function of the wavelength. Here actually there is a term zeta. Zeta is something which is called the size parameter, which is nothing but 2 pi r by lambda. R is the size of the scatters and lambda is the operating wavelength. It is 2 pi r by lambda, and scattering is defined in terms of the scattering parameter. So you can see in the microwave part of the electromagnetic spectrum, you are negligible scattering from the air molecules, attic nuclei, dust, smoke, haze, etc. But you have some scattering from the drizzle, raindrop, and hail. You have the scattering from drizzle and raindrops more at when the wavelength is larger. If you will move to the lower wavelength, you have more scattering. Compared to higher wavelength, you have the less scattering, but if you move to the lower wavelength, you have the more scattering. So, and the scattering, when the scattering is taken into this equation, that time scattering is introduced in terms of something called the phase function. Phase function has different forms. There may be scattering, there may be forward scattering, there may be backward scattering. Once the scattering reduced, it is equation become very complicated. Here I have shown you some of the forms of the phase function for different value of the zeta. That is 0.110 like that. So these phase functions are also calculated and added to this equation. But generally we don't use it if you are not working with the precipitation and the clouds. This figure is showing the sensitivity of the different parameters to them at different wavelengths. So you can see x-axis is the wavelength, frequency. X-axis is showing the frequency 10 gigahertz, 20, 30, 40 gigahertz, and y-axis is showing the sensitivity. That is change in the brightness temperature with respect to change in the parameter value. Yeah. So you can see the salinity has the sensitivity at very low frequency. It is at most of the salinity, but all salinity sensors instruments are operating at 1.44 gigahertz, that is L band, and that is the reason. Then it is also showing the sensitivity for the sea surface temperature, wind speed, cloud liquid, and the water vapor, atmospheric water vapor. When you are one more thing you have to take into consideration that this figure is based on rate transfer simulations, may not be the actual measurements. So when you are having the surface measurements, for example, if you are trying to measure the sea surface salinity or sea surface wind speed, you have to take into consideration that those frequencies are not affected by the atmospheric constituents, like or they are affected minimum by the atmospheric constituents like the water vapor, cloud liquid water, etc. India launched a satellite called the Megatropics way back in 2011, and it was actually decommissioned last year. But it has given a wealth of data. It was the Indo-French joint mission, and it carried two microwave instrument. One was the micro radiometer called the Madras. Another was the microwave sounder, that was the Saphir. I will talk about this sounders later part of my presentation. And radiometer has given number of parameters, including the precipitation, cloud liquid water, water vapor, wind speed. Those parameters were derived. You see, these instruments, they don't give the parameter directly. We have to develop the algorithms to derive those parameters. And we developed the algorithms and provided the algorithms on operational basis. So this is how the algorithms are developed and how we derive the different geophysical parameters. Here, if you will see this, the yellow boxes, here in the center of it is the ray transfer model. You have to have a ray transfer model. The ray transfer model provides you the radiances that are received by the satellite. It simulates the radiances that are received by satellite in terms of the brightness temperature. And what happens? You have the in the forward ray transfer model. You have the number of atmospheric parameters known to you. You have the surface conditions known to you. You have a transfer model, and you try to figure out what is the expected brightness temperature from the ray transfer model. But our problem is different. We have the brightness temperature measurement from the satellite, and we try to figure out that what are the atmospheric and the surface parameters that might have led to this value of the brightness temperature. So this is the inverse problem. Because brightness temperature measurements are few, maybe from 2, 3, 4 frequencies, channels, etc. Whereas number of geophysical parameters are many. This is an ill-posed problem. Mathematically, it is called the ill-posed problem. So generally, it is, for the retrieval, though it is possible to have the physical algorithm for the retrieval, but no operational meteorological agency applies the theoretical models for the retrieval. They apply the what we call it the physio-statistical models. So here what happens, we develop a database. Yeah. So here what happens, we have the atmospheric and the oceanic parameters we can have from the, say, NWP analysis. And we can give it to the transfer model, and we have a database of brightness temperature and the atmospheric parameters. Once you have that, you can add the sensor noise in it, because the sensors are not the noise free, and the noise figures are provided by the engineers who develop the instrument, and we add that Gaussian noise, random Gaussian noise in the measurements. And then we have some kind of physical or statistical scheme to relate the parameters with the brightness temperature. For that, we carry out a sensitivity studies. We see that which are the channels sensitive to a particular parameter and which are not. Those which are not the sensitive, we simply not use them. Those which are sensitive, we use them. And we use them in the scheme, retrieval scheme, and then the parameters retrieved. This is how generally the parameter retrieval is done. Here you can apply the AI based scheme, or you can have the simple regression, or whatever way you want. You can have a scheme, retrieval scheme, to retrieve the geophysical parameters. Geophysical parameters. This is all done when a satellite is not launched. After satellite launch, we see how these parameters, how our retrieval schemes are performing. And if we feel that they are not performing well, then we have to go back and do the necessary corrections. Because it often happens that whatever you have, having the considerations or assumptions, they do not work. And when the satellite launched, then we have to go back and do the whole thing again, or fine tune the algorithms to get the parameters right. Now, after the geophysical parameters, now moving to the precipitation. Actually, precipitation is a different ball game altogether. Other parameters, I have told you what is the scheme, how we can do that. But precipitation is more complicated. Because, here the scattering is now becoming important, whereas for retrieving the other geophysical parameters, the scattering was not important. And measuring the scattering is again a big problem, because the hydrometeors, how they are distributed and what is their shape, size, and so many things. I will come to that later part of my slide, in the next slide. Here, response of the precipitation with the planet temperature is also different. If you are operating at the low frequency at say 10 gigahertz or 19 gigahertz, your wavelength is much larger compared to the rain hydrometeors. Then you are in the low rain regime. But as the rain rate increases, the hydrometeor size is also increasing, and then you are no more in the relay part of the electromagnetic spectrum, relay regime of the scattering. You move to the Me regime. In the relay regime, the emission dominates over the scattering, but in the Me regime, the scattering dominates over the emission. So on left hand side, what you see is for 19 gigahertz, the brightness temperature increases with the rain rate because the emission is increasing. But after a certain point, it started decreasing because now relay assumption is no more valid. Now it has moved to the Me regime, where the scattering start dominating and brightness temperature start decreasing. Now, if you move to the 85 gigahertz, the another figure on right hand side, here the brightness temperature start decreasing right from beginning. Here what happens? The wavelength is small, and as a result of which, you are right from beginning, you are in the Me part of Me scattering regime, and where the scattering dominates, and as a result of which the brightness temperature start decreasing right from the beginning. And here what different curves you are seeing here on left hand side, they are for the different rain column depth, and then for different polarizations. The lower three curves are for horizontal polarization, and upper three are for the vertical polarization. On right hand side, what you see is they are for the different ice depths. Actually, what happens when you are moving to the 85 gigahertz, the scattering occurs mostly from the cloud top itself, where there is the ice. So ice particles, they scatter the radiations. It does not penetrate much. But if you are moving to 10 or 19 gigahertz, you have the more penetration and more, electromagnetic wave interacting with the hydrometeors. Whereas in case of 85 gigahertz, 157 gigahertz, you have the scattering only from the top of the clouds, and interaction. In fact, the penetration is very, very small. Now, for the rain detection, there are a number of problems in the rain detection, because one is, as I can say that this low micro frequencies are more suited for rainfall estimation, because the brightness temperature decreases with the rain rate, and you have over the land and ocean, you can have the algorithms working very fine. Here, but we have the different problem, because the size of the pixel is very large, as I have already talked in my slides earlier. There are other problems also, because brightness temperature increases with the rain rate, but brightness temperature also increases with the other atmospheric and the surface parameters. For example, brightness temperature increases with the SST, brightness temperature also increases with the wind, brightness temperature also increases with the cloud liquid water or water vapor. So it is very sometimes become very difficult to differentiate rain from the background. So particularly when the rain rate is low. Then differentiating the scattering emission signature, another problem. Surface dependency is always there for land and ocean. I'm not going into much detail of it, otherwise it will be a chapter, it will be a talk in itself. Then there is a horizontal rain variability, vertical rain variability, because if you have a pixel size of say 25 kilometer by 25 kilometer, then you cannot expect the rain is uniform over this 25 by 25, 625 square kilometer, it is a uniform. There will be some pockets where rain rate will be more, some pockets where rain rate will be less, and there may be some pockets where there may not be any rain occurring. So that creates a problem, because brightness temperature rain rate relationship is non-linear. Because of this non-linearity, there is some error, underestimation of precipitation occurs that we call the beam filling problem. And this is because of the horizontal rain variability, but there is also the vertical rain variability. Because the different types of rain, they have the vertical structure different, and electromagnetic wave is passing through the entire rain column, then this problem occurs. For example, the convective rain profile in the vertical may be different from the stratiform rain profile, and that also creates problem in the estimation. Then hydrometer size, shape, size distribution, etc. problem. And then rate transfer simulations, if you carry out the rate transfer simulations, that is, they are also not perfect. And there is always a validation problem of the precipitation, because satellite is giving precipitation over, say, 25 kilometer by 25 kilometer area, and we are comparing it with the surface observation, sometimes with the rain gauges, which are point measurements. So there is always representative error. We have done this retrieval for the Madras payload on megatropic mission, and this is some examples are shown here. Moving to the next. Now coming to the sounder. Again, going back to the rate transfer equation that we have already discussed earlier. Here, rate transfer equation is, suppose you are working in a very close to the absorption band, for example, because these sounders, they work very close to the absorption line. For example, this Saphir on megatropic, that was working close to the 183.31 gigahertz line of the water vapor. So if you are working close to the absorption line, say if you are working precisely at 183.31 gigahertz, what will happen? What the satellite will receive? The radiations. The radiations which are coming from the surface may not able to reach the satellite, because atmosphere is highly absorbing at this frequency. It will be absorbed by the intervening atmosphere. So the first term in this equation is no more valid. Now the radiations which are moving downward from each layer of the atmosphere, and then they are reflected from the surface and then going to the satellite, they will also not able to reach the satellite, because again the atmosphere is highly absorbing. So the last term is also gone. Now you are left with only one term. That is the layers of the atmosphere which are emitting and which are directly reaching to the satellite. Layers which are near the surface, they will also be radiating, but the radiations will not be able to reach the satellite, because again, as I said, that atmosphere is highly absorbing. You will get the radiations which are only coming from the top of the atmosphere. Otherwise, all layers below that will be radiating, but radiations will not reach to the satellite. Now you slightly move from, slightly go away from the absorption line, say 183.31, you go to plus 3 gigahertz. Say you move to 180 gigahertz. Absorption is still high, but not as high as it was at 83.31 gigahertz. Now you will have the radiations coming slightly from below the top layer, also reaching to the satellite. Now you also have to take into consideration the stratification of the atmosphere. The density of the atmosphere or particles which are contributing to the emission are more near the surface, and as you go up, they are reducing. So overall effect, if you will see, this is depicted in the figure here, the three figures here. You have the three frequencies here, for example, lambda 3 at the center of the absorption line, just coinciding with the absorption line, then lambda 2 slightly away, and lambda 1 is almost away. If you will see that how the transmission is varying, you will see that lambda 3, nothing is going to, nothing it is getting from the surface or the layers closer to the surface. Only top of the atmosphere you will be having, you will be receiving the radiances. Lambda 2, you have the more penetration, and lambda 1 can see up to the surface. Now, if you plot this here, what this called the weighting function, you will see that weighting function is peaking at different heights, different altitudes. So this is how a sounder works, because each frequency is providing the information from the different layers of the atmosphere. It is possible to derive the profile of the atmosphere, temperature or the humidity profile of the atmosphere. And this is called a weighting function, because here in this equation, if you see, This is weighted by the Planck function weighted by this term. So this is called a weighting function. Now coming to the Saphir macro sounder. Saphir had the 6 frequencies, all frequencies 183.31 gigahertz, and other frequencies were slightly away from it. And this is the weighting function, how they looked like. These are simulated weighting functions. And we use this to derive the water vapor humidity profile in the atmosphere. This is a sample of the humidity profile. I also talked about when I was talking about the radiometer, Madras radiometer on megatropic, I also talked about how we derive the precipitation from the Madras. But, Madras payload on a megatropic worked only for 14 months. Then it has some technical snag, and it was non-operational. Then after it was precipitation from the megatropic was not available. So we worked on it and we derived an algorithm for precipitation from the Saphir. And this is how it is shown here. This is the probability based algorithm for the rain identification. And then we have the ray transfer simulated precipitation algorithm for deriving the actual rain rates. Now, moving from passive to the active sensors. Active sensors, I am talking about is altimeter, spectrometer, centrifugal aperture radar, and GNSS radio occultation or reflectometry. Altimeter is basically a oceanographic instrument, and it is a very, very important instrument, and it is yes, the name suggests, it measures the altitude. Its principle is very simple. On the satellite, you have a radar. It sends a small pulse below it at the nadir, and that pulse is returned, and it measures the distance. You know the speed of electromagnetic wave. So you may think that this is a very simple instrument. There is nothing great about it. But there is a problem when you have to measure it with great accuracy. Present day algorithms have few centimeters of accuracy. For example, we have a altimeter on Saral Altica that provides an accuracy of about 4 to 7 centimeters. When you have the accuracy of 1 centimeter required, then your time measurement accuracy should be in the 30 picoseconds. So precise measurement of time is again a problem. And to have a 30 picosecond pulse, bandwidth requirement is 1 upon tau is about 30 gigahertz. That is not possible. So in order to achieve that, instead of a picosecond pulse, a nanosecond pulse is sent, and as a result of which the bandwidth requirement becomes 0.3 gigahertz instead of 30 gigahertz. But you can also have the microsecond pulse. But how it is achieved? Because your accuracy requirement for 1 centimeter is the picosecond pulse, but you are sending a microsecond pulse. This is achieved by the engineers by something called the pulse compression technique. They, instead of a square pulse, they send a chirp pulse and apply, using some technique, they what they call it, the pulse compression technique. Then you have a pulse of a microsecond that works as if it is a nanosecond pulse or picosecond pulse. So pulse compression technique is used to send the pulse, and then it is return pulse is stored in number of range gates, and that is how it is done. Here it is pictorially shown. A pulse is now sent to the surface. It has not reached the surface. As soon as it will hit the surface, the energy start growing. That is the return energy return signal waveform start growing. As the pulse intersect more and more to the surface, more energy it start growing here, and then it becomes constant, and ultimately there is a plateau, and energy falls. Now, the half power point here give you the sea surface height measurement, SSH, and which is a very important parameter. And this pulse is, as I said, stored in number of range gates, and the slope of this pulse the slope of this leading edge of the pulse, that gives the significant wave height, and the total energy that is returned after scattering from the surface provides the wind speed at the surface. So altimeter, the most important parameter is the sea surface height. For that you have to know the high altitude of the satellite very precisely. That is done by the ground-based laser stations, and one laser on satellite that is called DORIS. On most of the satellites it is there. On our Saral Altica and Indo-French mission, the DORIS was also there. So that provides the height of the height of the satellite very precisely with respect to the ellipsoid. Then you have the measurement R, that is the measured by the altimeter, and you also have to know the geoid. If you know the geoid and the height of satellite very precisely, and the satellite measured range, then you can measure the sea surface height. And sea surface height, if it is known, you can measure the what is called the pressure gradient force, and you can measure the geostrophic current, because the geostrophic approximation, this pressure gradient force is balanced by the Coriolis force. So that is how these measurements are done. But in order to do that, you have to do many corrections. You have to do the correction for the atmosphere, water vapor, dry atmospheric correction, and many other corrections. I'm not going into all of them here. They are shown here in the right hand side of it. Altimeter, we have the Saral Altica presently working, and we have the sea surface height measurements, which can provide the, as I said, which can provide the geostrophic current over the oceans. We have the significant wave height from the leading edge of from the slope of the leading edge of the return pulse. And we also have the wind speed measurement from the Saral Altica. Now coming to the Oceansat 3 series, which is recently launched. And this Oceansat 3 was launched in 2022 November, and it is carrying a KU band, a scatterometer. And this scatterometer is actually called the pencil beam scatterometer. This is an active instrument, a radar, and it has two rotating antennas. One antenna, they are swapping the concentric circles on the surface, as you can see in the figure here. The radar, this is the antenna which is swapping the inner circle, is HH polarized, and the antenna which is swapping the outer circle is VV polarized. HH polarized means the H polarized wave is sent and H polarized wave is received. VV means V polarized is sent, V polarized is received. And the swath of this, or say the diameter of this circle, the smaller one is 1400 kilometer and the larger one is 1800 kilometer. This is operating in the KU band at 13.5 gigahertz. So this scatterometer is operating at 13.5 gigahertz. Now, scatterometer is a radar, as I said. This is the radar equation. You can see the first equation, the radar equation. From the radar equation, it depends upon the lambda, that is the operating wavelength. PR is the power received. Left hand side, PR is power received. That depends upon the wavelength, operating wavelength, then transmitted power, antenna gain G, then back scattering coefficient sigma 0, R is the range, and A is the target area. From this equation, it is possible to calculate the sigma 0. Now, sigma 0 depends upon so many factors. It depends upon the operating frequency, depends upon the incidence angle. It also depends upon the way the ocean surface wind speed and wind direction, polarization, etc., etc. Though it is possible to model the sigma 0 theoretically, but in practice it is not done. The reason is that many parameters which are required to model it are not very accurately available. For example, we don't know the directional wave spectrum of the ocean waves. precisely to get the theoretical measurement of the wind. So there are other parameters as well, which are not very precisely known. So it is empirically done. And there is an empirical relationship, sigma 0 is equal to A plus B cos phi plus C cos phi, where A, B, C are the wind speed, direction, incidence angle dependent constant. Phi is the angle between radar look angle and the upwind direction. So this is available in the tabular form. All the agencies, whether it is NASA or whether it is ESA or whosoever, they use the tabular form of the model function to convert to get the wind speed and direction from sigma 0. However, there is a harmonic dependence of sigma 0 on wind, as you see on the right hand side. The upper figure is for H polarization and lower one is for the V polarization. You can see at any wind speed, you have the sine wave like structure. That means same value of sigma you have same value of say wind speed, you have the two different directions. So in order to remove this ambiguity, we require the number of measurements of the sigma 0 to overcome this ambiguity. That is why, spectrometer, we have two concentric, two antennas which are swapping the concentric spheres, and one is VV polarized, another HH polarized. Now you assume any area on the sea, you will see that first it will be seen in the forward direction. Then it will be seen that the area will be seen in the afterward direction, and with VV polarization and with HH polarization. So you have basically 4 observations of any part on the ocean to have this. So with the 4 such observations, we are able to remove the ambiguity and we are able to provide the operational wind measurements from the spectrometer. This is the wind measurement from the Oceansat 3 spectrometer, and here you can see the wind for I think 2 consecutive days, and right hand side is for over a cyclone, and lower figure are the comparison with the ECMWF analysis. It is the comparison of scats and wind product with the ECMWF. The left one is the comparison of the wind speed. Right one is showing the wind direction. So what we are getting with respect to the ECMWF, the RMSE is 1.40 meter per second in the wind speed, and the wind direction we have the RMSE of the 14.38, and this is what we had prior to the launch. This is the accuracy of the wind measurement that we had defined prior to the launch, and we have achieved these accuracies. We are trying to further fine tune it, and we may have even better accuracy in future in the next version of the data product. Now coming to the centric aperture radar, how much time I have is left for me? Yeah.
Actually, we are neck to neck, but I know this is your 25th slide, so you continue. Maybe little faster would be helpful.
Okay, so I think the SAR may be after the SAR there may be one more slide for this radio occultation. Okay, so centric aperture radar, as I said, that in microwave you have a very poor spatial resolution because the beam width is very large, but that can have an advantage also. And how it is this is taken, this advantage is helps making the resolution better. Now assume that you have a large beam of which is having a covering over an area on the surface, say about 10 kilometer or say 20 kilometer. You have a target. So when the satellite is moving for a considerable time, you have the target within the beam. So at say time t1, that target enters in the beam, and after a time t2, that target leaves the beam. So you have, and during this time, you will keep on receiving the echo from the target. they will be shifted. You have the Doppler shift because the satellite is moving, but it is possible that you can process the data and you can synthesize a aperture which is much bigger than the aperture you are actually having, the antenna aperture. So this is the principle of the centric aperture radar. So in the centric aperture radar, the processing is done such a way that the target echoes are currently summed up to achieve very high resolution. But when the centric aperture radar sees the ocean, there are different type of effects or processes. They define the intensity of the image. One is that ocean is comprising of the waves of different wavelengths, and small waves ride over the large waves. And since SAR is working in C band or KU band, so most of the scattering is occurring because of the very small wind-driven waves. They are a few centimeter size because of something called the Bragg scattering. So it is sensitive to the waves which are of the same order as that of the wavelength. So small waves we are talking of, but these small waves are riding over the large waves, as you can see in the figure on left-hand side. So because they are riding on the large waves, so this can change the local incidence angle due to the local facet normal. As a result of which, it is also possible to study the swell or observe the swell in the radar image. So this is shown here, left-hand side. It is called the tilt modulation. Then comes the hydrodynamic modulation. These waves are associated with the orbital motion. That means water particles are moving up and down in an orbital fashion. And in that case, there are regions of the convergence and divergence associated with the wave, large wave. Where there is a convergence, you have the sea rough, more rough. Where you have the divergence, sea is less rough. So this also affects the intensity of the image in the image plane, and thereby one can study the large wave, their wavelengths and all. Then there are other effects also which are called the velocity bunching. Now satellite is moving, and the Doppler shift which is occurring because of the satellite movement is taken care by the processor, onboard processor. But if the target is also moving, then it can create some problem. So here in this case, if target is moving in the azimuth direction or it is moving in the range direction. If it is object is moving in the azimuth direction, then what will happen? It will add additional Doppler to the processor. It will provide additional Doppler to the processor. But that is actually, if not taken into consideration, then the image may look defocused. And same time, if it is moving in a range direction, then it changes the time at which the zero Doppler frequencies encountered related to the stationary object. So what happens if the object is moving in the range direction? You will see that image is shifted in the image plane. Often you will see in the SAR images over the land, particularly. This can be seen over the land. Sometimes you will see the train is going over a track. You will see the train is shifted from the track. So that is happening because of this problem. Because of the object moving in the range direction will be shifted. So these are the effects. But SAR images can be used for many atmospheric oceanic studies. One important application is that you can have the FFT of the image. You can have this, do some corrections and all. You can have the ocean wave spectrum. You can see the internal waves. Those SAR cannot, electromagnetic waves do not penetrate the surface of the water, sea, but still you can see the internal wave because internal wave has certain signatures on the surface. So those signatures can be seen by the satellite image, and from the SAR you can achieve very high resolution of say about 10 kilometer. So that is possible. And apart from that, SAR can also be used for many atmospheric studies. Here, for example, seeing the atmospheric fronts, And some people have also studied, cyclone structure and all using the SAR data. India has a RISAT satellite launched in February 2022. These are the specifications. Now we are going to have NISR mostly next year in January. And this is the NASA ISRO Sensitive Aperture Radar. We are jointly developing with the NASA. This is having the two frequencies, S-band and the L-band. L-band SAR is being provided by the NASA, and S-band SAR is being provided by contributed by the ISRO. So this NISR will be launched next year by January, hopefully. Now coming to the GNSS, as I said, that this is not unlike the other radar systems, which are the monostatic. This is the kind of bistatic. This uses the GNSS satellites, and you can see the GNSS satellite on the right hand side of the figure, and left hand side is a low orbiting satellite, which is carrying only a receiver. So you can see the signal from the GNSS satellite. There are some positions, particularly when GNSS and the low orbiting satellites are on different sides of the Earth, and they are ascending or descending with respect to the satellite. Then in that case, the GNSS signal passes through the atmosphere, and during this process you can have this signal as it passes through the atmosphere. Depending upon the temperature and the water vapor present in the atmosphere, it will be refracted, and it is therefore possible to construct a refracted index profile of the atmosphere using such measurements. If you have the refracted index profile, you can have the measurement of the temperature or the humidity profile. If the temperature profile is known, you can measure the humidity, or vice versa. So this is how the signal is used to do the GNSS signal is used to do the to measure the atmospheric profile of the temperature and the water vapor. This is one way it can be used. Another way, this is called occultation, radio occultation. Another way it is being used is called the reflectometry. GNSS signal is reflected from the surface, maybe ocean surface, or from the Earth surface. Here I would like to inform that GNSS is working in L-band, and it is not affected or very less affected by the hydrometeors in the atmosphere. So it is almost giving the all-weather measurements. So here occultation I have already talked about. Reflectometer means it's a signal reflected from the surface, Earth surface, maybe ocean or the land, and it is received by the satellite. If it is reflected from the ocean, it is possible to measure the wind, because the reflected signal intensity depends upon the sea state. If sea state is very rough, then you may not able to have the signal coming directly to the satellite, given the optical geometry. But if sea is very calm, you will have more energy coming to the satellite. So and this sea state in turn depends upon the wind speed. So it is possible to measure the wind speed over the ocean. So that is how the GNSS meteorology is present day. It is very popular, and people are working on it to have the better measurement of the water vapor, in the atmosphere, and also the window in the atmosphere, window over the ocean. And this is important because GNSS can provide wind which are not affected by the rain. So under the severe weather conditions like cyclone and all, it is possible to use the GNSS for measuring the wind over the ocean surface. Now some of the applications. These microwave measurements are used for the cyclone studies. particularly for cyclogenesis, center estimation, track prediction, intensity estimation. My colleagues have done number of studies. This figure lower, the central figure, the figure in the center. This is the brightest temperature from the Saphir. You can see, you can very easily identify the center of the cyclone, its eye wall and cloud structures, etc. Then you can have the wind measurement from the scatterometer. You can overlay the wind scatterometer measurements over the INSAT image. Here also it has identifying the cyclone center, and you know cyclone center identification is very important for its track prediction. So the center identification can be easily carried out. Then also the Rmax can be calculated, the region of the maximum wind, using the brightest temperature data from the macro radiometer, where you have the very cold region. If you move in the radial direction from the center of the cyclone, and where you have the coldest brightest temperature in the high, say 85 gigahertz, you can assume that the region is having the maximum wind speed.
Sir, application part, if we can do little quicker for the application.
Yeah. But almost I am coming to end.
Because there are a lot of questions.
Yeah, another 2-3 minutes only.
Yeah.
This is the NWP modeling, how the observations are, different observations have contributed to the NWP numerical weather prediction modeling. And this I have taken from the ESA site, and you can see that the microwave measurements, particularly the radiometer and the GPS, etc., they have a big contribution in the NWP modeling, radiances particularly. Then this is showing the forecast sensitivity to the observation impact, that how much each measurement having the impact in the weather forecast. You can see again the microwave. Here the black curve is microwave water vapor that has the highest sensitivity, forecast sensitivity to the observation, but other microwave measurements also have very high sensitivity. This is also some. This I can skip, I believe. Yeah. Then we have also assimilated the microwave radiometer from the megatropic in the WRF model, and we try to see the impact of it. We have seen that we have shown it. This paper is actually published in Quarterly Journal of Royal Meteorological Society, that it has shown very positive impact when we assimilate the microwave radiometer TPW and wind speed in the WRF model. And this data is our satellite data, and products are available from our website called https://monstack.gov.in. You have the all kind of data, L1 data, L2 data, L3 and L4 data available. L1, what are the L1, L2, L3, L4 data? That is examples are given here. Then we have this NWP forecast. We also run the NWP model on experimental basis, and that also we provide through our website forecast. We also have the climate model for the monsoon forecast, and image-based forecast like nowcast and real-time observations also we provide. We also have, ISRO has got the 3 radars at TULS, Char and Cherrapunji. We process this radar data and process data, and as well as geophysical parameters also we provide through our website. ISRO has another website also, vedas.sac.gov.in. These are the Space Application Center website. Other than that, NASA, NRSA websites you all might be knowing. I am only talking about the Space Application website. There are 2 websites. One is for the meteorological oceanography satellite data. Another is for other land applications. So we have the 2 such websites. Thank you. Here I end.
Thanks a lot. I mean, most probably we learned each and every details of microwave-based remote sensing. I mean, thanks for all these details talks. Now there will be a question session. Before question session, it's a photo session for the panel members. So I request everyone to switch on their camera. And sir, could you close your PPT? Then it can come in a screen. Yeah. So now I request Dr. Archibald Yar, Dr. Thablelji, yes, Dr. Kiao Moe O, if you can switch on your camera. Taggi sir, please switch on your camera. And Mohan, please take the photograph when.
Taggi sir, please. Just a minute.
Yeah, all Dr. Q, it is not focused. Okay, your camera.
Yeah, I think everyone now all right.
Yeah, I think it has been done.
Yeah, fine. Just a minute. Okay.
Thanks a lot, Dr. Mohan. Now there will be interactive sessions. The moderators are Dr. Madan Sigdel from Tribhuvan University, Nepal, and also an active member of SAMA, and Dr. Dibba Prakash from Purnima University, Jaipur, also the most active member of this satellite meteorology activity. So now I request both of them start the questions to the speaker.
Thank you. So, first of all, thank you so much, Atul Varma sir, to give very light speech on and give the very detailed lecture on the topic. So there are a large number of questions, more than 20 questions. So I am taking one question. So there is one question is it possible to obtain surface wind speed over land from any of the satellite product? And if it is not possible, there are any proxies for the same using the satellite product?
Yeah, you see, over the ocean, it is possible because of the wind effect on the ocean waves. For something called very famous Cox and Monk work in early 50s. Thereby, they have related the sea surface slopes to the wind speed. There is no such relationship possible over the land, and so it is very difficult to measure the wind over the land. Then the different type of terrains, different types of structures over the land. So it is, as on today, it is not possible.
Thank you, sir. And second question is, what is the area beyond the sea coast from which stratometers can scan the ocean surface to give out wind vectors?
Yeah. See, what we are providing is wind at 12.5 kilometer and 25 kilometer. So it is better if you are away more than 12.5 kilometer because in that case you have the pure ocean pixel. Otherwise, you have there is possibility that part of it will move over the land, and then you have the problem. But here experimentally we are also working with finer resolution also. Maybe in future we will have a more finer resolution measurements. In that case, you can reach very close to the coast. But as on today, this is what is available.
So there is one question of Dr. R.R. Kelkar, sir. Is there a way to retrieve atmospheric pressure at sea level?
Yeah, it is. I will say that it is not something which is impossible. There have been some instruments suggested in the theory. There are one or two papers they have talked about it. Otherwise, when you have the wind measurements from a scatterometer, for example, indirectly you can measure the areas, regions where you have the high pressure, low pressure, like that, but may not be so precisely in quantitative term. But qualitatively you can always make out. But there are some papers I have seen in the literature that it is possible, though we don't have any instrument right now to do that.
So next question is, what are the minimum resolution of atmospheric satellite? Is it freely available? And there is one more addition in question is, if not, then what is the minimum resolution for freely available data?
There is, my talk was about the microwave remote sensing. So microwave, you have the limitation. Otherwise, in optical, you have very good resolution available. But here I will not talk about the optical. I will talk about only the microwave point of view. Microwave centric aperture radar can give you a very good resolution of a few meter. But the only thing is, there are limited number of applications of centric aperture radar. But if you go to the micro radiometer, for example, you have to live with the constraints that are imposed by the antenna size. We may not be able to carry very large size antenna, so the resolution is poor. But new techniques are coming up. For example, as in case of the centric aperture radar, there are some technique developing which are called the centric aperture radiometer, and their concept is different. Of course, I have not talked about it. And for example, this L-band radiometer, which is presently on a NASA satellite, they have the resolution of say about 25 kilometer. That is with the centric aperture. But centric aperture radiometer resolution is will not become the in meters. It will be in tens of kilometers instead of 40-50 kilometers.
So now over to you, Madan sir.
Okay. Now I will see some of the questions in the chat box. So next question is like this. Is it possible to use Madras product to see phenomena for a local city?
Madras is a micro radiometer. Though you can have the measurement available over the land, but resolution is again 25 kilometer. So you will have only one pixel over a city. So I don't know whether it will be of any help to you, because if you have this 25 kilometer size pixel, then it will not be. I think it may not be of any use to you.
Yeah. Okay. Next question is.
Then I will add to it. Yeah, I will add to it. See, Madras worked only for 14 months. Then after it has a technical snack. So you have the data available only from 2011 October to 2013 January. That is
yes. Okay. Next question is: isn't the microwave system applicable for digital elevation?
Yeah, that is possible. You have this, the microwave imagers. You can anything you can form as an image, and you can put images in a sequence. Then you have the animation. So that is possible, of course. But only problem is that microwave is not giving the continuous observations in a particular area like the geostationary satellites. Geostationary is stationary at one point, and you have the continuous observations every 15 minutes, 30 minutes, like that. Microwaves are put in the low orbiting satellites. They are not geostationary, and they keep on moving around the Earth. And because of the because they can be put only in the low orbiting satellites, they cannot be put in geostationary. Otherwise, resolution will be too bad. It will be of no use. Now, with this constraint, you have the measurement today. You may have another measurement after say 24 hours or something. But over a month, if you will have the 30 observations or 50 observations, you can always put them together and see how the things are changing with the time.
Okay, next question is like this. He asks to explain about the microwave sensor saturation and how it impacts the heavy extreme rainfall events.
Yeah, actually, microwave is very useful for extreme rainfall events. Unlike the optical, for example, thermal infrared is indirectly measuring the precipitation. You measure only the cloud top, and you try to infer what is happening below the cloud. That is how the thermal infrared is working, because thermal infrared is not penetrating the cloud. On the other hand, microwave can penetrate the cloud. It can interact with the hydrometeor, so it is more direct compared to the thermal infrared. And because it is more direct, it is more accurate. Only thing is that you have the measurement at 25 kilometer resolution. And intense rain has property of having high rain with strong horizontal gradients. So you have the very strong rain happening in a 5 kilometer, 10 kilometer area, but strong gradients. So but microwave give you the average picture in that case. So that is the limitation. Otherwise, microwave is naturally more direct compared to the thermal infrared or visible.
Okay, thank you. Next question is, can sea surface height anomalies be used to measure storm surge height and coastal flooding or submergence of island in the light of increasing sea height in the global warming regime?
Yeah, that is possible because, microwave radiometer, in fact, this for coastal flooding and all, centrifugal aperture radar is the best instrument because of its high resolution, and it is being used. We have a hydrology group here in Space Application Center. They are observing and providing the flood, such kind of information from the centrifugal aperture radar, which has very high resolution and can provide the information about the coastal region. When you have the water at some area or flooded some area, the emissivity changes drastically over that region. As a result of which, it is very easy to identify the flooded region. So that property can be used to do that. Radiometer also being used, but radiometer resolution is poor. If it is flooded over a large area, then you can do that. Otherwise, radar is a good instrument. This centrifugal aperture radar is a good instrument to carry out such studies. I will suggest him to visit our website, that is vedas.sat.gov.in. There he will get more information about this.
Okay. Next question is, how does the satellite lifetime is estimated? It depends on the sensor or power input to the satellite.
Yeah, actually, this depends upon how much fuel is kept there, because satellite, though it is put in an orbit, but gravity is always working on it. So just keep on trying to pull it down. So you have to maintain the satellite in a particular orbit, and this is done with several ways. One is they have this small rockets there to put it in a motor there to put it in a place, and there that uses the fuel. So this all depends. Generally, lifetime of you can assume 6 to 7 years is the nominal lifetime, but some of the satellites have worked more. For example, we know that TRMM TRIM satellite, which was launched in 1997, and it lasted till 2013. So that way, it is possible that some of the satellites, they last more, if they, but generally nominal life is about 5, 6, 7 years. That's all.
I think, Dr. Madan, I think we can consider another 2-3 questions, and then we'll complete these questions.
Okay, now I like to request Dr. Deepa Prakashji for a few questions to ask Dr. Varma.
Thank you. Thank you, sir. So there is one question is it possible to measure thunder activity in an area numerically from space using sensors?
Yes, that is possible, but microwave may not be, I think I should not restrict myself to microwave here. Microwave itself may not be, is of limited use, of course, but my colleagues are doing it. And, thunder activity, when there is a thunder activity, there is sudden growth of the clouds. And if you have the continuous monitor area, then you can identify the, such areas where there is a sudden rise in sudden growth of the clouds. So thermal infrared images are being used for this purpose. One can see that how this brightness temperature is changing in the thermal TIR, and if it is changing very rapidly, then it is possible that this is growing. In fact, my colleague has developed the method for this nowcasting of the heavy rain events. And this we have reached to the matured level, and we are operationally providing through our MOSTEC, and we have transferred it to IMD also.
So there is one question. Could you please tell the difference or importance of Oceansat 3 and other spectrometers? Yeah,
in fact, the Oceansat 3 spectrometer and earlier spectrometer launched by India, that is SCATSat 1 or Oceansat 2, they are basically working in the same frequency, that is the KU band spectrometer, and most of the electronics is the same. Only thing is we are able to achieve better signal to noise this time, as a result of which it may provide better estimation of the sigma 0, and which in turn can provide the better estimation of the wind speed. So that is the only difference. Otherwise, if you see the other configurations, then they are more or less same. That means they are pencil beam. They have the same kind of swath. They have the same type of same frequency, same incidence angle, etc. Only thing is because of the advancement in the engineering, better signal to noise is achieved.
So, sir, within the time limit, I am asking the last question. What electromagnetic spectrum is suggested for ecosystem health studies in the ocean course to study effect of between ocean and extreme events on coastal plantations?
Yeah, when you are talking of the coastal area, I know coast is very important because most of the human activities are, in the coastal region. But macro radiometer of lesser help because of the poor coarser resolution. So I think the synthetic aperture radar kind of instruments can be more useful for studying the coastal ecosystem and all.
So thank you, Dr. Dibya Prakash and Dr. Madan Siddel. Now it's a time for vote of thanks. So I would like to invite Dr. Mohan Kumar Das, Director of NOAMI, and also the Joint Secretary one of SAMA.
Sir, one request from my side. There are some questions are remaining, so we can send to sir by email. So
Okay, if sir agrees, yeah.
yeah.
Yes, sure.
Okay.
Anytime.
Thank you, sir. Thank you.
Thank you.
Thank you.
Thank you, Dr. Swagata Paida. A pleasant evening to everyone. We extend our heartfelt thanks to all the participants for their invaluable contribution to the success of our session, focusing on the basics of microwave-based remote sensing with meteorological satellites and their practical applications. Our deepest appreciation goes to our distinguished guest speaker, Dr. Atul Kumar Varma, sir. Knowledge guide. Dr. Atul Kumar Varma stands as a foremost authority in the field of using meteorological satellites for microwave-based remote sensing. His extensive knowledge and expertise have shed light on your understanding of this essential field. Respected figure. Dr. Varma's remarkable career and unwavering dedication to meteorology have rightfully established him as a respected figure in this domain. His dedication has advanced our understanding of microwave remote sensing techniques. Gratitude for Dr. Varma. We genuinely thank Dr. Varma for generously sharing his knowledge with us. His insights have enhanced our understanding and will undoubtedly inspire further progress in this field. Acknowledgement of organizers. We also express our appreciation to the event organizer for their careful planning, which provided us with an invaluable platform for learning. Looking forward, as we contemplate the insight from this session, we are inspired by Dr. Varma's wisdom and the collaborative spirit of our discussions. Together, we eagerly anticipate a future where microwave-based remote sensing with the aid of meteorological satellites continue to enhance weather forecasting and environmental monitoring with sincere appreciation. Thank you. Thank you all.
Thank you. By this, we would like to conclude the session. And we can stop the YouTube streaming. But after that, if Tyagi sir or Somesh sir, if you want to say something.